Hello. Today we're going to talk about vectors. Hopefully most of this will be a review from last year. For instance, if we have a vector that's pointing upwards from the x-axis at a given angle theta, hopefully we all remember that this is actually made up of two components, one that goes in the x direction and one that goes in the y direction. So I'm going to label this vector as vector r. I'm going to use a little arrow above it to indicate that it is a vector quantity. So that means that this is our x, and this is our ry, our x component and our y component. And so to actually solve for the different components, we can say Rx will equal vector r times cosine theta, and vector y will equal r sine theta. So notice I use small arrows above the r to indicate that r is in fact a vector quantity. If I have our two components, rx and ry, I can find the magnitude of vector r by using Pythagorean theorem. So I can say vector r will equal the square root of rx squared plus ry squared. But this doesn't give me the actual vector quantity. This just gives me the magnitude of vector r. And so I'm going to use brackets around it to indicate that it's just a magnitude. It's not the entire vector because this magnitude is missing direction. So without direction, it's not a vector quantity. It's just a distance. So in order to find the direction, I have to find the angle that it's pointed at. And I can find the angle using one of our trig functions. The easiest one in this case is going to be tangent theta, where tangent theta equals our y quantity over our x quantity. So we can solve for theta by saying inverse tangent will equal ry over rx. So hopefully this is all a review from last year. So this year, we're going to talk more about unit vectors. Unit vectors are a very important dimensionless vector its sole purpose in life is to specify direction. These vectors have a magnitude of 1 because they're purely just to point us in the right direction. So we can look at an example of our unit vectors. We have 3 unit vectors that we're going to work with this year: I, j, and k. And these unit vectors pretty much replace x, y, and z. And so we can see over here on our x-axis, we use our unit vector I. And notice all of our unit vectors have a little hat over the top of them. And that's to indicate that they are in fact unit vectors. On the y-axis, we use unit vector j, and on the z-axis, we use unit vector k. So I, j, k just replace x, y, z. And so all 3 of our unit vectors are exactly the same length, they just point in different directions. And so down here, we can see that the magnitudes of each one of our unit vectors all equal 1. So to use this unit vector notation, it simply replaces our subscripts x, y, and z, since those can get very messy and hard to keep track of. And so instead of writing something as ax equals 4, we would instead write it as 4i. And then we put a little hat to indicate that it's a unit vector. And so we could do this with all of them. Instead of a y or a z, we instead say 5j or 6k. And so this is how we want to denote our vectors. The number gives us the magnitude, and then the letter gives us the direction. So we can use this to replace our x and y notation. So if we had this point right here that was at 4, 5, 5, rather than using our standard Cartesian coordinates, we could rewrite this as 4I plus 5j. And we put our little hats above the I and the j. And so again, it's just a different way to write our vectors. And this is really, really helpful when we have more than 2 dimensions, such as 3, 4, 5 dimensions. So, we can also use this notation to easily add vectors. And generally, when we write vectors, we want to use this notation because it makes vectors much easier to work with when they're when they're already broken up into their components. So for example, if we have vectors A and vector B, and we want to add them together to get vector R, all we have to do is add together the x components and the y components. And that gives us our vector R broken up into its x and its y axis, or components. If we wanted to find the magnitude of vector R, we can use the Pythagorean theorem, and that will give us the magnitude of vector R. And then of course we can find the angle, the direction, using tangent as well. So again, using this ij notation just makes vectors much easier to work with. We can also use this same process in more than 2 dimensions. We can use it in 3 dimensions, 4 dimensions, 5 dimensions, as many as you want. And so again, if we have 3-dimensional vectors A and B, and we want to add them together, all we have to do is add the x components, the y components, and the z components. So we get our vector R in terms of I, j, and k. And again, if we want to find the magnitude of vector R, we can use Pythagorean theorem. Pythagorean theorem also works in more than 2 dimensions. Here we're using it in 3 dimensions, but we can also use Pythagorean theorem in as many dimensions as you can think of. However, to find the angle of vector R, it's a little bit more difficult. And so instead, we're going to use this definition, which is our definition for a dot product, which we'll talk about dot products a lot more later in the year. But for now, we can say that our vector R will make an angle theta with the x-axis equal to inverse cosine of the x component of the vector divided by the magnitude of the vector. And so we take the magnitude from right here that we get from Pythagorean theorem, and then we use the x component that we found up here to give us the angle with the x-axis. And so again, we can use this same framework to add as many vectors as we want to. If we want to add 3 or more vectors, all we do is we add the x, the y, and the z components together. And then we continue to use Pythagorean theorem, and so on and so forth. So, I have an example problem for you guys. I want you to work it out. It's a pretty straightforward problem, but I want you to work it out using vector notation. And then I want you to work it out on a separate sheet of paper and turn it in to class. Hopefully, this has all been pretty straightforward. If you have any questions, please do not hesitate to ask.